All right, so we ended off yesterday talking about Oersted and Faraday. Okay, and Oersted and Faraday, they were the ones who kind of were studying the relationship between electricity and magnetism. Okay, Oersted's contribution obviously has to do with the development of the electromagnet. Okay, and that electricity can produce magnetic effects. Okay, and he discovered that by accident with the compass. Okay, but the fact that electricity can produce magnetic effects is also important. Okay, in terms of our ability to broadcast, transmit, and receive electromagnetic signals. Okay, that is radio. Right? Any form of radio waves, cell phone, obviously classical radio. Okay, if you listen to the radio in the car, that kind of radio. Okay, Wi-Fi, any sort of wireless transmission ability. Okay, it finds its basis here. All right, so that was a really important discovery in terms of our ability to do that. And then Faraday, he developed the first electric generator, discovering that the opposite is also true, that moving magnetic fields can cause movement of charges, okay, and moving charges are electric currents, which we use obviously in harness to run electrical devices. All right, so he gave us the ability to generate electricity using a magnet, which is essentially what all turbines allow us to do. And really, there's only a couple of power generation methods that do not involve the use of a turbine and a classic Faraday-style magnetic generator. Okay. Now, when you have a turbine, just so that we're clear here, okay, a turbine is essentially a spinning wheel. All right. So if you've ever seen like pictures of like those old flour mills that had the water wheel, and the river would turn it, that's essentially a primitive turbine. Okay, anything that turns and is attached to something that will then move back and forth, okay, is essentially a turbine. So a dam, okay, a hydroelectric dam is always going to have turbines. Water falls through the dam, hits the turbine, and the turbine spins. Coal-fired plants and nuclear plants work on the same principle, and they both heat water into steam, and the steam turns a turbine and generates electricity. Wind turbines, okay, so the big propellers that you see down at Pincher Creek, okay, when those propellers spin, they spin a turbine that's inside, and that again alternates the magnet moving and generates electricity. Really, tide power, okay, there are places now that are experimenting with essentially what look like wind mills, except they're underwater. And as the tide comes in, it pushes the turbines, and as the tide goes out, it pushes the turbines the other way, and it can generate electricity there. So places that have big tides, okay, are looking at using those to generate electricity because it's essentially pollution-free. And it's not disturbance-free. Obviously, it would disturb the tidal area to build those things, but it's pollution and emission-free. So all of those essentially involve turning a turbine. Now, when we say turn a turbine, we're also pointing out that we're converting one form of energy to another. Okay? We're taking what we call mechanical energy, so that's something that's moving, right? And we're using that movement to create another kind of energy. Not so much to create it, but to convert it into something. And every time you do an energy conversion, a little bit of energy is lost. Okay? And it usually turns into heat and other things. So yes, we can convert one form of energy to another, and we're always doing that, but the more conversions there are, the less efficient that process becomes. Okay, which is why wind turbines and hydroelectric dams and things like that are relatively efficient. There aren't that many conversions in between. But a coal-fired plant or a nuclear plant, there are more. Because in a coal-fired plant, first you're turning chemical energy into heat. And then that heat is being turned into mechanical energy, and then the mechanical energy is being turned into electrical energy. So there's a bunch of conversions in between, and energy is lost at each step. The fewer conversions you have, the more efficient it is. So having a wind turbine is way more efficient because the wind turns the turbine. There's only one conversion. Okay, everyone follow there? All right. So anyway, Faraday, super important, okay, because he allowed us to generate reliable, constant sources of electricity. Okay, now, another one that came up shortly thereafter, shortly after Faraday and Oersted, was a guy named Seebeck. Okay? He understood this idea that, well, the more energy conversions there are, the less efficient something becomes. So since heat's always a byproduct of every conversion, why can't we just turn heat directly into electricity? Okay? The answer is we can, but it's awful. Okay? It is so incredibly inefficient as to be prohibitive. It means it's just not worth doing. Right? We don't want to generate electricity from heat because heat is the lowest form of energy. All right? We can turn heat directly into electricity without the use of a turbine, but you get so little electricity that you'd have to have so much heat, it's just not worth doing. Right? Now, that doesn't mean that his discovery isn't useful. It's not useful for generating electricity, but it is useful for protecting electrical devices and circuitry. Okay? Essentially, what Seebeck discovered is that when you have enough heat within metallic current-carrying metals, okay, you can generate a current. This is how he proved it. Okay? He took a candle and he heated up this apparatus. So he had a compass needle, okay, that was kind of in between here, all right, and he had it so that it was pointed north, which would be kind of into the page here, and he had this copper kind of horseshoe-shaped thing here, and then he had this plate of iron. Now, copper and iron have different abilities to conduct heat and different abilities to conduct electricity. When he heated up the iron, okay, we know that that means that the particles in the iron began to move faster. Okay, because when things heat up, their molecules and particles go faster. Okay, that movement, okay, was transferred to the copper, and when the copper began to receive that movement, copper conducts better than iron does, and as a result, the electrons began to flow more quickly through here. So he had a current moving through the copper. Okay, now he knows that because what happened to the compass needle after a little while of heating? Right, it turned. It turned and followed the wire. The problem is, he didn't get very much current. Okay, he burned like a whole candle and got practically nothing out of it. Right? So yes, he produced an electric current, but not enough to really power anything. But we use this idea in circuit breakers. Okay, you probably all have like a breaker box, a big electrical panel in your house, okay, that protects your house from essentially burning to the ground. Okay, that's the job of your circuit panel, is to prevent electrical fires from starting. Electrical fires start because too much current runs through a circuit. When too much current runs through a circuit, heat builds up in the wires, enough usually to start nearby things on fire. Okay, what a circuit breaker does is, when there's enough current that there's heat starting to build up, the small electric current made by that heat trips the breaker. Okay, it essentially causes a little motor or a little thing to click and open the circuit up so that no more electricity can flow through it, and then the heat dissipates because there's no current anymore. Everyone follow there? So it's essentially what we call a thermal couple. Okay, a thermal couple is something that can generate a weak, small electric current when there's enough heat present. Okay, when there's too much heat present, obviously then we want the current to stop because we don't want our house to burn down. Right? So that's essentially what he developed there. So Seebeck made this thermoelectric converter, or thermocouple, okay, that could convert heat to electricity, but again, it's not something we use to generate electricity, more as a protective device. Okay. Now, nuclear and solar energy. Okay, we're grouping these two together. It might seem odd, but the reason we have solar energy is because of nuclear processes. Okay, the sun is essentially a big giant nuclear fusion reactor, right? And its energy obviously travels, okay, hundreds of millions of kilometers through space to get to us. Now, obviously, when people first looked at the sun, they said, oh man, that's bright, I shouldn't look at that. Okay, and then they said, it looks like a big fire in the sky if I look at it for a long time, and then I see spots in my eyes and things like that. Okay, but obviously it does. It looks like a big fire, and when we see even modern pictures of it from spacecraft that are studying it, it does. It looks like a big fire, and it is. But it's not a chemical fire, and that's what people early on didn't understand. They looked at the sun and said, there's a big fire in the sky. All right, and they pictured like a campfire. Well, for a long time, people believed that's what the sun was this big fire. The problem with that idea is that the amount of fuel you would need for that fire would run out after about 5,000 years. Okay? The sun couldn't last if it was actually a chemical-based reaction type of fire. Right? So they had to come up with something else, some other thing that the sun, that could be fueling the sun other than a chemical fire. Okay? What we discovered is that it's nuclear energy. Okay, it's fusion. The sun is made of hydrogen, and the sun is massive. Okay, it is hundreds of times larger than all of the other planets in the solar system combined. All right, if you added the masses of all the planets and all the asteroids and comets and everything in our solar system together, it would be hundreds of times, even maybe thousands of times smaller than the mass of the sun. The sun is unfathomably large, okay, and unfathomably heavy, even though it's made of the simplest, lightest material in the universe, hydrogen. All right? because it is so massive, it gravitationally pulls all that hydrogen together, and there's so much heat and pressure because of that mass that the hydrogen fuse together. Okay, and they fuse and they become helium, and that releases lots and lots of energy. Now that process will run for probably effectively anyway, for about another 5 billion years. So you don't have to worry about the sun going out anytime soon. Okay, that process will run effectively like that for a while. But then the sun will essentially start running out of hydrogen. But it's got lots of helium. It's got a fair amount of mass. It'll start fusing helium. But when that happens, the sun is going to change radically. It will swell, become very, very big, and swallow up the inner planets. And we better be gone by then, because there'll be trouble. Okay, but it's essentially a big nuclear reactor. Okay, now for nuclear energy, okay, unfortunately, it took a long time to learn about nuclear energy because the people who studied it died young. Okay, especially in the early going, because they didn't realize how bad it was for them. Okay, they were playing around with these, radioactive rocks. I mean, they just look like little chunks of metallic-looking rock, right? And they're like, playing around with it and whatever, but it's radioactive and it's killing them slowly, and they didn't really realize that at the time. In fact, they have a museum piece of Henri Becquerel's desk, okay, from his university days when he was a professor. And if you walk past it with a Geiger counter, one of those things that makes the clicking sounds when it encounters radiation, 200 years later, his desk is still hot. Okay? Yeah. His desk, it doesn't have any of the stuff in it anymore. His desk is still radioactive. All right? 200 years later, imagine sitting in that desk and be like sitting in an X-ray machine for days on end, right? You just wouldn't do it, but these people did because they didn't know. Okay, same with Marie Curie. Okay, Marie Curie was a brilliant scientist. She learned lots of things, studied lots of things about radioactive materials and the energy that they could give off. Unfortunately, they were always giving off this energy, and by the time she was dead, she practically glowed in the dark. Okay, because there was just so much of this radiation that was unfortunately affecting them. All right, so Henri Becquerel observed that certain atoms spontaneously disintegrate. All right, and that's what we call, if something is radioactive, that's actually what it's doing. It's breaking down into smaller, simpler atoms because its atoms are so big that they're not stable. The problem is as pieces of the atom come off, they release energy that was formerly holding those pieces on. That's radiation. All right? So the energy that's released as the neutrons and protons kind of come apart, that's the energy that gets released as radiation. Some things are way more radioactive than others. All right? But everything to some extent has a little bit of that ability. All right? But obviously the bigger the atom is, the more unstable it will be. All right, so certain atoms, okay, for nuclear energy here, certain atoms spontaneously disintegrate and in that process emit radiation or radiant energy. Okay, now nuclear energy is potential energy. All right, it's not a kinetic energy, it's potential because it's stored in the nucleus of an atom. It only gets released when the atom breaks. Okay? Or when you put two atoms together, right? So there's the two kinds here, right? So this kind of whole last two sentences of this paragraph are pretty important. Okay, when the nuclei of two atoms combine, or the nucleus of an atom is split, okay, then we get that. Okay, so again, important that we know that that kind of energy is available. If we can speed that process up, it not only releases radiation, but it also releases heat. Okay, and that's why we can use nuclear fission as a source of a way to generate electricity. It releases lots and lots of heat, okay, and that can be used to turn water into steam and turn the turbine. Okay, so when you use nuclear power, in terms of mass of fuel, nuclear power uses way less fuel than, let's say, a coal-fired plant generating the same amount of electricity. Right? So what's the drawback besides Chernobyl? Okay? What's the drawback? I mean, obviously, if you're not using very much fuel, you shouldn't be producing very much waste. Well, you're going to produce a lot of energy, but you don't produce very much waste, at least in terms of mass. Yeah. Okay. The waste that's produced is so much more toxic, okay, than the waste produced by a coal plant. Now, I'm not saying that carbon dioxide isn't a problem. Okay, when you burn coal, you release carbon dioxide and soot and all that kind of stuff, and that certainly contributes to the greenhouse effect. But you're putting out tons of that stuff. Okay, you have a nuclear power plant, and you produce the same amount of electricity, and you produce a barrel full of waste. The problem is, what do you do with the barrel that's glowing? Okay, I mean, it doesn't really glow. It's not like The Simpsons. Okay, it's not this glowing green goo that comes out of barrels in Homer's office. But okay. It is still highly radioactive. And I don't mean they put it in like an oil barrel. Okay? The barrels you store nuclear waste in are initially an oil barrel. And then concrete is poured around it. Okay? So it's sealed in concrete, put in these barrels, and then put in a cooling tank. Okay? It's essentially just water. Right? That stuff's not generating any electricity. They just put it in the water so it doesn't get unbelievably hot. The water can absorb a lot of the heat energy that's put off. Now, once it cools, it's still radioactive. So they can't just say, oh, well, it's not hot anymore. Just put it out in the back. Okay? Because if anything happens to that container, that stuff gets out. It gets into the environment. It's really bad. We saw that after the tidal waves hit I can't remember the name of the reactor there in Japan that got flooded, okay, by the tidal waves. But they're still picking up radioactive isotopes in Vancouver, okay, from that event. So this stuff lasts a really long time. It doesn't break down in nature, and obviously it's highly toxic. Not poisonous toxic, but radioactive toxic. All right, so those are kind of a big deal in terms of what do we do with that stuff. All right. So again, it's a great source of energy. It's really efficient in terms of mass, but what do we do with the waste? Well, there's a few places in the world where you can store that waste. Okay? They dig essentially a really deep hole. And I don't mean like with shovels. Like they drill a really, really deep hole that's, let's say, thousands of meters deep. Okay? And it has to be into a certain type of rocks with certain types of properties so that if and when the containers containing the radioactive material decay and break, the radioactive material can't get into groundwater, soil, okay, and things like that. Essentially, they're buried so incredibly deep that that can never happen. All right? Once they fill up those storage places with the barrels, then they fill it in with concrete. Okay? So it's really expensive to get rid of the nuclear waste. All right? The other problem is it's not cheap to build a nuclear power plant. And a nuclear power plant is only good for, let's say, at the maximum amount, 50 years. After that, you have to close it down. Okay? You have to build another one. It's not like a coal plant where you can just fix and replace parts as they break down. In a nuclear power plant, the area around it just eventually gets to the point where you got to shut everything down and you got to stop. Okay, unless you want the fish to be glowing, okay, in the river and things like that. All right, and they have a few examples of that around the world where they ran a nuclear power plant for too long, and the area is now essentially sterilized. All right, obviously Chernobyl would be one of those places. The Hanford nuclear plant in Washington, okay, it's kind of out in the middle of the desert, essentially in Washington, but the area around it, nothing grows. No one can live there. All right, they just ran the plant for too long. They didn't realize, right? Things are better now. People realize a little more, and there's better protective measures. But okay, you still can't run a nuclear power plant forever. So it's not as good of an investment as cheaper ways of kind of generating electricity. All right, now solar energy. Everybody says, well, the sun's always around. You know, solar energy is a great way to generate electricity. Okay, and to an extent, they're right. Solar energy is always available, but it's not. It doesn't generate as much electricity as people think. At least not in terms of how much area it would take up. Right? A coal plant, I mean, it's a large building for sure. It doesn't take up huge amounts of land, though. You want to have an effective way of generating solar power in significant amounts, you need a lot of panels. Right? Look at Drake Landing. Right? I mean, they're like, well, the solar-powered enclave. Well, they're not 100% solar-powered. They're certainly significantly solar-powered, but every house's roof is covered with solar panels. Okay, that's a lot of space. If you go to California, where they actually do generate some electricity with solar power, you see what they call the power farms. Essentially, it's land that you couldn't farm because it's a desert. Okay, but the ground is covered with panels. Okay, like a farm would be covered with crops. Here, they're covered with solar panels. So it covers a lot of ground, and that's habitat for certain types of plants and animals and things like that. So they're not without their their costs for certain. Okay, yes, it's not polluting to an extent when the panels are no good anymore. They do have stuff in them that's not good, okay, and things like that. So solar energy is nice, but it's not as nice as everybody thinks it is. Okay, so solar energy results from, okay, this fusion reaction, okay, and the release of nuclear energy, and then it travels to us as electromagnetic radiation, travels through the vacuum of space, reaches Earth, and then its high energy particles, called photons, can be harnessed. So when these high energy photons strike a solar panel, okay, they act pretty much the same way that a plant would act. It excites the electrons that are in the materials in the solar panels, and they move to a higher level of energy. Okay, remember we talked about that kind of one of the first days in this course. And then when those electrons fall back down to a lower energy level, that's what essentially generates the electricity. Okay, and it's great as long as you have constant sunshine that's intense, okay, and things like that. It's difficult in Canada to use solar power, right? At least effectively, for a few reasons. First off, the sun we get isn't direct, okay, especially in the wintertime when the Earth is tilted away from the sun. Okay, and you'll notice that in Drake Landing, the solar panels are all on one side of the roofs. Has anyone ever noticed that? Okay, they don't have solar panels on the north-facing side of the roofs because the sun doesn't shine on that side of the roof. Okay, the sun shines on the south-exposed face. Okay, so you can't have them everywhere, right? Just because of how far from the equator we are. And in the wintertime, they're only getting energy for 6 hours a day if they're not covered with snow. Okay, so there's all kinds of things to consider in terms of practicality. Solar power is wonderful if you have good sun, constant sun, intense sun, okay, which we don't always have here, right? So it's not really practical for us. All right, questions on that? Okay, now motion and energy. Motion and energy, okay, this is kind of that, again, that conversion of mechanical energy, which is energy of motion and position, into other forms, okay? And this was kind of, other than chemical energy, one of the first types of energy to really be studied because it was easy to study. You could watch it happen. All right? It wasn't like radiation where you sat in front of the rock and didn't realize it was slowly killing you. Okay? This stuff you could actually see. You could see it happen. As an example, okay, we've got Newton's cradle here. Okay? How many people have seen one of these? Right? Yeah. You pull the ball away and it goes click, 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 click. Believe it or not, that almost got Newton killed. Okay? He invented this thing, and then he showed it to people. And at the time, leaders in kind of religious positions didn't like things that, they were very closed-minded, not like they are now. In terms of when he did that, they said, "You're a witch." Okay, because people believed in that kind of stuff then, right? Okay, and so he pulled this thing away, and it hit this thing, and then this one went up on the other side, and they're like, "Witch." He's like, "No, you could do it." "I'm not going to do it. I'm not going to get burned at the stake. You're a witch." Okay, and he actually got in a lot of trouble, and he had to come up with really quickly an explanation for why this was happening. And luckily for us, that was sort of the birth of the idea of what he called the living force, okay, which we could now call energy. Right? The ability of something to do work, okay, and exert a force through a distance and all that kind of stuff that we talked about yesterday. All right, so this group of English scientists watched a demonstration of Newton's cradle. It caused great concern. They had no idea why the ball on the opposite side rises to nearly the same height as the first ball. Okay, at the time there were no theories. So this guy named Gottfried Leibniz reasoned that whatever caused the ball to move resembled a force that could be transmitted through. Okay, and he said it's kind of like dominoes, right? If you stack up dominoes, you don't push the domino at the end, you push the domino at the beginning, and that energy or that living force is transferred through to all the others. This is really not a lot different than that. Nobody says you're a witch when you knock dominoes over. Okay, so that was kind of how he explained it, right? So he's really the person who came up with the sort of framework for this idea of mechanical energy. Okay, so he's kind of the one who explained Newton's cradle, okay, to people. And more importantly than that, okay, he came up with the types of energy that we came up with yesterday, okay, and that is kinetic energy and gravitational potential energy. Right? He didn't actually call them that, but he's the first person who kind of put those ideas on paper. All right, so we're going to say here, he realized that there's two types of energy that could be observed in nature. Okay, things like flowing water, okay, or anything that, or wind, or anything like that, okay, could be used to do work, and thus had kinetic energy. Kinetic means anything that's moving. So, if you're thinking like later on in life, you might take kinesiology. That has to do with the movement of the human body. And kines means to move. All right, and then for number 2 here, okay, the second type of energy is that any object raised above the Earth's surface has the potential to do work. The example we used yesterday was the hole punch. Okay, as soon as I picked it up off the floor and put it on the table, I had done work, and it now had the potential to fall off the table. And if it did that, it could do work on my foot or the floor or whatever happened to be below it. Okay, and so that was what we call now gravitational potential energy. And those are the two types of energy that we're going to work with most in Science 10 and in Physics 20 for that matter. All right, now he also realized that one of these could be turned into the other, and that it was possible for an object to have both kinds at the same time. Right? So as an example here, when this hole punch is sitting on the table, right now all of its energy is potential because it isn't moving. But if I was to freeze it kind of in time as it was falling, okay, it would have both. Because it would still be a little ways off the ground, but it would also be in motion, meaning it now has some kinetic and some potential. So he said, since it can have both, we would add them up, okay, and call the sum of those two energies mechanical energy, right? And that's, again, the kind that we'll deal with most in Science 10. All right, then heat and energy. Okay, obviously people wanted to be able to use heat to do stuff. That was kind of really important because heat was always readily available. Taylor? Yeah. Okay, so they said there's got to be a way, or a relationship at least, between heat and energy. All right. So we have the ancient Greeks. They had this idea. They had no knowledge of the concept of energy, but they knew what heat from, or had an idea what heat from fire was. Okay. They called it, the movements of these tiny particles within a substance. Okay, and stuff like that. So they were, sort of partially right on that. Okay. Joseph Black, okay, observed that when a cold object is placed in a cup of hot water and then removed, the object becomes warmer. Mind-blowing, right? Duh. Yeah. Of course, when you put something cold in something hot, it gets hotter. All right? But here's the importance of that. It showed that energy only flows one way. Okay? You can't transfer coldness to something, but you can put something in that will absorb heat. This is what we do with ice cubes. All right? You want to keep a drink cold, you put ice in it. But you're not transferring coldness to the object, or like to the drink. You're absorbing heat from the drink. The ice has less energy, less heat than the drink does. So heat naturally flows from hot to cold. Okay, that was Joseph Black's kind of big contribution, was doing some experiments that showed heat is always flowing from hot to cold. Cold is not flowing from cold to hot. Okay, there's no such thing as cold. There's less hot and more hot. Okay, because it had to do with this idea of heat energy. So that was Joseph Black's big deal. Okay. Unfortunately, Joseph Black was wrong about a couple of things. This goes back to the problem of energy is not something you can put in a jar. Okay, it's not something you can put in your hand. It's not matter, it's energy. He said it must be an invisible fluid. It was always convenient to say, ooh, it's magic or invisible or whatever, because you couldn't really explain it, so you just explained that it was invisible. Okay? It was this invisible fluid. Well, the problem with it being an invisible fluid is, even if it's invisible, it's a fluid. It still has to be then matter, okay? Which means it has to take up space and have mass, and it doesn't. All right? But the fluid idea helped him to explain how it could flow from one place to another and even through other objects. Okay, so he was right about that. Okay, he said that it flows naturally from hot to cold things. All right. It was this idea, okay, that led to our development of this science here. Okay, the flow of heat from one thing to another is called thermodynamics. Right? Thermo means heat. Dynamics means change. Right? So this is changing heat, moving heat, transferring heat. Okay, that's the science of thermodynamics. Okay, Now, here's the other thing, and this is an important kind of clarification here. We often say heat's a form of energy, and I've even said that a bunch of times here this morning, which is actually not true. Heat is the transfer of thermal energy. What we typically call heat is actually thermal energy, right? But I mean, up to this point, it hasn't been really important to make a distinction between the two, okay? But heat is the transfer of thermal energy in the same way that work is a transfer of mechanical energy. So when we say heat, we're actually talking about the movement of thermal energy from one thing to another. All right, everyone with me there? So there's no such thing as heat energy, there's thermal energy, and that's what we're going to start using as the proper terms here. Okay? Now, after this idea here of heat transfer, people wanted to see how do we convert mechanical energy to heat, which is easy because it always happens, okay, and vice versa. How do we convert heat to mechanical energy? Well, this guy here, Benjamin Thompson, who for some reason changed his name to Count Rumford. I don't know why you would do something like that, but okay. He was born in America, but he moved to Bavaria to become the Minister of War. I guess that's a good gig, I don't know. Okay. Anyway, his job was he supervised the construction of cannons. Okay. Building a cannon is actually not all that complex. You take a big chunk of metal and you bore it out with a big drill, okay, so that you make essentially a tube in it, okay, or a barrel, and then you put the powder in, and then you put the ball in, and then you light the fuse, and when the fire gets to the powder, it explodes, and the expanding gases propel the cannonball out of the cannon, right? Okay, that's kind of same as how a gun works. Okay, a gun works the same way. You ignite the gunpowder, and the expanding gases can't get past the bullet. Okay, they push the bullet through the barrel, it spins and comes out the barrel at a high rate of speed. Okay, so that's kind of how that works. Anyway, he noticed, and we have to give him credit here, also invented the coffee break. Okay, that the people who were boring out the cannons could boil kettles of water on the top of the cannons while they were boring them out, with no fire. Okay, so what they would do is they would have essentially a big drill bit, okay, that they would all be on turning manually like this. Okay, so they'd be rotating this thing, there'd be a whole bunch of them, and they'd be boring out this cannon. So little shavings of metal would come out, just like when you sharpen a pencil, okay, that kind of thing. Those shavings of metal would come out. Now, is there a lot of friction if you have one metal object turning and grinding on another one? Yeah, okay. Does friction generate heat? It does. Okay, they would get so hot while they were boring out these cannons that if they put a kettle on top of the cannon while they worked, after a short period of time, the water in the kettle would boil. All right. So if you worked hard enough, you could have a break because you could have your tea. Okay, so that's why we say he invented the coffee break. Okay, so these people would drill these things out, and then they'd get tired. Why would they get tired? They're working hard, right? They're transferring energy from themselves to the drill, which is then working against friction while it bores out the cannon. Well, that energy has to go somewhere, okay? And where it goes is to heat, okay? So essentially, they were doing all this work to boil water and make cannons. But, I mean, essentially, all that stuff was getting turned into heat and boiling the water in their tea kettles. All right? So he proved from this and kind of studying it that you could turn mechanical energy into heat. What he didn't realize is you were also going chemical energy to mechanical energy to heat, because the people themselves were the place where the energy was coming from. They were the ones turning the drill. All right, so it's one type of energy converted to another, okay, along this kind of chain of things. All right, so he noticed that the supply of heat was endless so long as the workers continued boring the hole. As soon as they stopped, the kettle stopped boiling. All right, because now all of that work isn't being done anymore. There's no more friction, there's no more metal parts rubbing together, okay, and the heat would be gone. As soon as it got back to work, thing would heat up again. It was a dangerous place to work, right? You didn't want to just, oh, I'm tired, and lean against the cannon. You're getting pretty bad burn. If it's hot enough to boil water, you kind of had to be careful. It'd be a very hot and kind of unpleasant work environment. Okay? All right. So if people believed Black's caloric theory of this fluid, okay, the cannons should run out of energy because he believed the fluid was part of the mass of the object. Well, as you bore out a cannon, it should have less and less energy, but as long as those people kept that drill moving, okay, there was always a supply of energy, which led Rumford to believe and to discover and put on paper that you could transfer energy from one thing to another, provided you had that energy to give. Okay? So heat and mechanical energy were different types of energy that could be converted from one another. That was kind of Benjamin Thompson or Count Rumford's big thing there. Okay, and then a little bit later on, a guy named Thomas Young linked this mechanical energy idea to the kinetic and potential stuff, and basically said that an object can have both kinds. They can have both potential and kinetic energy at the same time. Okay, so Thomas Young is the one who came up with the current definition of energy, which is energy is the ability to do work. Okay, pretty simple, right? But obviously, it's something we understand. Your parents say, go out and mow the lawn. I don't have any energy. I don't want to do that. Okay, and now you're lying, because obviously you have energy because you're alive. Okay, but we say, I don't have any energy. I don't feel like doing any work. Well, that's the strictest definition of energy. Energy is the ability to do work. If you don't have any, you can't give it away, right? Which is why the definition of work is linked to that. Work is the transfer of energy. You can't do work if you don't have any energy to give, okay? And if you don't have any energy to give, you can't do any work. So yeah, it's like chicken, egg, which came first, right? All right. Last thing. Probably the most important guy, Joule. He's got to be the most important guy. The units for energy are named after him. Okay, the units for energy are joules, so he must have done some pretty important stuff. Well, he did. He's the one who quantitatively measured, using experiments, showed that you could turn one form of energy into another, and then mathematically proved that it had happened. Okay, so he showed quantitatively with numbers and math that yes, this is what's going on. Okay, now his experiments, believe it or not, were actually very simple. Okay, they didn't involve any complex machinery or anything like that. Okay, what he did is very simply showed that potential energy, okay, the energy of position and due to gravity, could be turned into heat. Right? And he did that with this falling block experiment. Right? So he had these two blocks. He had this block here that was stationary, essentially hanging from the ceiling on rods that couldn't move, and he had this block that was the same size but that could move on these kind of cables. So he would pull this rock up and away. All right? And when he did that, he had just done work. Right? That block previously would have had less energy because it wasn't moving, couldn't fall any further, whatever. When he pulls it up and away, he gives it energy. And people said, how do you know that? It doesn't look any different than it did down here, except that it's a little bit higher. And he said, well, let me prove it to you. When I drop this block and it hits this one, this block will get hotter. Okay? So, let's go. The block comes flying down, smashes into the stationary block. Temperature of the stationary block goes up. Okay? He proved that this block had energy as a result of it being moved to this position. He quantitatively showed that. All right? Now, you could do this at home really easily. Take a piece of wood and take a hammer. You don't need a nail. Okay? And just take the hammer and bang on the piece of wood. Just hit it 10 or 11 times. Put your thumb where you were hitting. It'll be hot. Well, maybe not like scorching hot, but it'll certainly be warmer than the rest of the board. All right? Because you have transferred energy to the block. You've converted mechanical energy of the falling hammer into heat. Okay? You'll also probably have a little dip and deformation of the block. All right? So he proved just using that experiment, and based on how much the temperature went up, he was able to calculate the energy transferred to the block. Okay? Everyone kind of follow me there? So his math was solid enough that people said, oh yeah, sure, yeah, there was energy there. Okay? And here's how much energy was there. And he had a similar one with this apparatus, which basically had these falling masses that would turn these little propeller blades that are inside this jar here. They would spin as these masses fell, and as they spun, there was air resistance within the jar, okay? And that caused the temperature of the air inside the jar to go up as these masses fell. Not a lot, but enough. Okay? Again, proving that raising something above the ground required energy. And he proved that they have the energy because now I'm going to use that energy to heat something up. All right, so he proved this kind of relationship between mechanical energy, okay, and heat that other people had sort of started on. Okay, so Jules experiment, okay, supported the connection between potential energy and heat. Okay, as the masses fell, the wheel rotated, okay, and that heated up the water or air, whatever was in the jar. Okay, and it was the same, okay, as the falling block idea. Okay, so this was essentially the experiment that allowed us to use mechanical energy to generate other types. Okay, I mean, a hydroelectric dam works on exactly the same idea. Just instead of producing heat, it produces electricity. It uses the potential energy of falling water, okay, to make electricity. Okay, in your notes you have these questions here. You don't have to do them all, just the circled ones. All right, so you're going to use the stuff that's in the notes and the stuff that I've talked about here with you today, okay, to answer those questions. I want to be able to go over those questions by 10 o'clock. Okay? All right, have at it there, guys. Okay, guys, let's go over these here real quick. Okay, so for number 2, first of the following scientists describe his invention, the type of energy the inventor was able to produce, and how it was produced. Okay, so what did Ørsted make? Okay, that was his experiment, in that he showed that an electric current can produce magnetic effects. So essentially he produced the first electromagnet, right? Okay, that was his invention. He produced the first electromagnet, showing that electricity could be converted to magnetism. All right, that was what his invention showed. All right, for B, okay, Faraday, what did he do? Daniel? Right. He invented the generator, the electric generator that showed that magnetism could produce electric currents. Okay, he moved the magnet in and out of the coil of wire, made the electrons move, and generated current that way. All right, Seebeck. Okay, showed heat could be converted to electricity, and his invention was circuit breaker, thermocouple, yeah, okay, that kind of thing. All right, what about Edison? I didn't mention him specifically, but Edison invented the light bulb, okay? And the light bulb showed that electricity could convert and produce light and heat. Yeah, I mean, Edison's original light bulb, right, was the old filament style kind, you know, with the glass bulb and the metal thing that goes across on the inside. We don't use them much anymore because they're really inefficient. They make more heat than they do light, and they use up a lot more energy. So now we use like LEDs, and well, hopefully not too many of us use the CFL ones. They were really popular for a while, but now people are discovering that you're not supposed to throw those away because they have mercury in them, and that's really bad. Right? But yeah, certainly the original light bulb was Edison's idea. Okay, and he kind of has a claim to fame of being the most successful failure ever. Right? Because he tried and tried and tried to make the light bulb. He came up with he failed probably 300 times. Okay, to try and make the light bulb, and succeeded once. And everyone says, "Well, do you consider yourself a failure?" And he says, "Nope. I discovered 299 ways how not to invent the light bulb." Okay, so he's definitely like a glass half full kind of guy. Okay. All right, Volta. What did he discover? Jacob. Right, he invented the first battery. Showed that chemical energy could be converted to electrical energy, okay, using different materials that would have different chemical properties. All right. Practical use, well, we've kind of talked about that already for number 3. Yeah, obviously electromagnets can be used, for switches. They can be used for, obviously picking up big, heavy metallic things, okay, and stuff like that. But magnets are also used in speakers, okay? Electromagnets are what make speakers move back and forth, right? We talked about that yesterday. Okay. For Faraday, obviously electric generators have really one use. They make electricity. Okay, Seebeck, we said that his invention today is more used for like circuit breakers and electrical protection. Okay, Edison, his invention still does what it did originally, light the darkness. Okay, and Volta, I mean, we're still using batteries in different forms, but essentially still the same thing. All right, for number 4, difference between nuclear fusion and nuclear fission. Adam? Right. Nuclear fusion combines atoms to form larger atoms and releases the energy of the previous atom state. And then nuclear fission is the energy released when you break an atom, or an unstable large atom breaks down on its own. Okay. Number 6, what's the modern theory of the source of energy for the sun? Well, nuclear fusion. Okay, the fact that hydrogen is compressed under incredible gravitational forces, okay, in order to force it together to make helium. Okay, for number 9 here, the contributions the following people made to the nature of heat. What did Sadiq Carnot do? I didn't talk about him specifically, but he was in your notes. Right, he was part of Jules' stuff. Okay, basically helped him out with a lot of that, or did some of the precursor work for Joule. Okay, for James Young. Nobody noticed that the first name on that is wrong. It's supposed to be Thomas Young. There was no James Young in any of your notes. I don't know why it says James there, but there's no James Young in your notes. Thomas Young, okay, was the guy that he did a lot of the stuff with kinetic and potential and mechanical types of energy there. Okay, and Joseph Black, okay, similar. Okay, had a lot to do with kind of the precursors of thermodynamics. He was the one who said, hey, did you know that when you put something cold in something hot, it gets warmer? Right? He was the rocket scientist, sort of. Okay, but he showed that heat does flow from hot to cold. Right? And then Count Rumford, okay, he was the guy that did the cannons and found that you could convert mechanical energy into heat, and that the source of that mechanical energy could be, you know, people moving a drill or whatever. As long as there was movement there, that movement could be turned into other kinds of energy. All right, number 10, how Joule proved that heat could be produced from potential energy. Well, he had the falling mass experiments, the 2 of them, the one with the jar full of water with the blades in it, and the one with the 2 the falling block and the stationary block. He showed that when he did work to lift that block up, that when he released that block and it smashed into the other block, that work that he did became heat energy absorbed by the stationary block. Okay. Now, in his experiment here, the manipulated variable would have been the amount of work that he did, okay, or the height to which he brought the other block, the falling block. That's what he manipulated. He gave energy or put energy into the experiment. The responding variable would have been the temperature or thermal energy of the stationary block, okay, and anything else would have been controlled. He would have had to use the same blocks, be the same mass, lifted to the same height, okay, whatever, right? All those kind of things would have to have been maintained. Okay, for number 12, in these situations, identify the major form of energy involved. Antacid tablet placed in a glass of water, tablet starts to bubble. Bubbles are an indication of what? Could be heat, but if we think back to chemistry, of a chemical reaction, right? So this is chemical energy, right? Generally, an acid tablet doesn't make the water much hotter, okay, but it does make mechanical energy in the bubbling and fizzing, and it kind of plops around inside. Okay, for B, a fluorescent dial on a wristwatch glows at night. Light energy, actually. A fluorescent dial, okay, if most fluorescent dials, okay, I mean, yes, they use electricity, but they're giving off light energy. All right. For C, a downhill skier begins to ski downwards down the slope with increasing speed. Okay, started out with potential, but as his speed increases, he has more kinetic. We could have also said mechanical energy because it would encompass both of those. Okay, tingling sensation on the tongue when it's touched to the terminals of a 9-volt battery. Anyone ever done that before? Back in the day before we had battery testers, that's how we used to check if the battery was still good. You get a good shock there. Okay? Which type is it? Batteries give you electrical energy, right? Okay. Yeah. E, the inside of a car gets extremely warm if the car is left in the sunshine. I'd say there's 2 possibilities here. Solar and thermal. Yeah, heat. Okay. A seagull lifts a clam high above the beach. Yeah, so motion would be mechanical energy, probably mostly potential if we're just talking about the height of the clam. Okay, but we could also say kinetic because the bird is probably also moving. Otherwise, it would fall out of the sky. Okay, and for G, a compass needle held over the surface of the Earth points north. That would be magnetic. Yeah. Okay, for 13, describe an appliance or machine that for its operation requires the following forms of energy. Chemical. Well, anything that burns fuel. All right, lawnmower, car, okay, anything like that. Light, anything solar powered, right? If you got solar panels on a small calculator, okay, or something like that. Okay, heat, okay, anything that can absorb heat and do something with it, okay. Electrical energy, your hair dryer or tea kettle, okay, coffee maker, whatever. Okay, magnetic, compass, okay, things like that. Okay, and describe an appliance or machine that produces the following forms of energy as it operates. That's a tough one. Something that produces chemical energy? Plants. I mean, it's not a machine, but it's the only thing I could think of that actually makes chemical energy. I mean, you could say a refinery makes chemical energy, but the stuff it had at the beginning also had chemical energy. So, okay, anything that makes light, well, light bulb. Okay, thermal energy, basically anything that converts one form of energy to another is going to make thermal energy because it's always released as a byproduct. Okay, but you could say a heater. Okay, electrical energy, a generator. Okay, magnetic energy, an electromagnet. Okay, I know those seem kind of simple, but they're also right. Okay, tomorrow we're going to be talking about thermodynamics. Okay, it's obviously Friday tomorrow, so shorter class. What's due tomorrow? Plant research project. Make sure you have that done for tomorrow.